Hello. In this section, I would like to show you some structure of language model, and would like to know what if we would like to modify the language model by using some extra structure, so that the language model can learn even more knowledge, so that when you perform your downstream task by using the customized language model, the we anticipate such kind of modification can make the language model to perform better on some specific downstream task. So I would like to show three structures. Okay, that is the first one. Okay, let's first take a look at the black lines. Okay, so the black blocks and black lines, they are original language model. So let's take a look at the left hand side. Originally, we will have text, right? Input text, and most of the time they are English, right? So when we pre-train a language model by using, for example, Wikipedia documents, books, articles, and the first things we need to know is we need to build a dictionary, right? So we need a tokenizer. Tokenizer need a dictionary. So most of the time, the English word may have more than 3,000, 7,000, even 10,000 words. And we mentioned it before. Most of the time, we will select a proper size of a dictionary, and the rest of the words which is not in the dictionary will be marked as unknown, right? And although of course there are some special tokens like padding, like COS, to represent the start of the sentence. SEP means separate, okay, to separate different sentences. So we need a tokenizer, which includes a dictionary. Okay, to build a dictionary, it depends on what kind of articles, books, Wikipedia document that you input. Okay, so follow the black line, and we can see that the tokenizer will tokenize the sentence into tokens, okay, or what we call word pieces. Okay, we mentioned word pieces last week. So of course the sentence starts with COS token, right? And for example, the tokenizer will be the word tokenizer will be tokenized into two word pieces. The first one is token, and we use sharp to represent that there are some words after token. And tokenizer will be the second word pieces of tokenizer will be izer, I-Z-E-R, and here we have sharp, okay, to represent these two words are connected, but the tokenizer split it into two different word pieces. Okay, so most of the time we will have, for example, 256 or 512 tokens as the input of your language model. So the black one is the very big language model. Take the bird transformer, for example. We will have 12 different layers of the transformer and attention, right? So language model will be very large. Let's assume the weight, which is the red one, okay, the red weight is trained by Google by using MLM, which means mask language model. In other words, by using closed test. Okay, so Google will use billions of sentences collected from the network, books, and trying to perform closed test on this language model to find the optimized weight, which is the red one. Okay, the red one. So that is, and for the language model, every input token will have an output. Okay, but usually in practical we use the first output, which is corresponding to COS input. we use this specific output as the representation of the entire input sentence. So that is the black one. Okay, we talked about the black one before. Okay, since Google use Wikipedia and books to train a model to obtain the optimized read weight, this weight is it can understand what English is and to know how to analyze a sentence. Okay, so that is English, right? But in our context, we would like to perform some fine-tune task so that the language model can understand more about, for example, cybersecurity. So let's take a look at the green lines and blocks. Okay, so at the left-hand side, we can prepare lots of cybersecurity document. As we mentioned before, there is some cybersecurity framework, right? We introduced MITRE attack framework, right? So there will be 14 different attack tactics, and we can collect those documents, and we have more than 400 attack techniques and sub-techniques, so we can collect all those security related documents. So after we prepare those documents, okay, the green blocks, we can perform fine-tune, and we use the original tokenizer, right, to tokenize the document into word pieces. Okay, there's a very important feature of BERT and transformer is that once you have a tokenizer, since the tokenizer uses word pieces to analyze the sentences, so even if there is some strange or new word in your cybersecurity document, it is still okay for BERT tokenizer to tokenize your sentences, even if it is a very strange word or a new word, because BERT tokenizer most of the time the tokenizer will not simply just output unknown token. They will try to split your strange words or professional words into word pieces. Okay, so after that, again, to perform fine tune, we can run MLM, which is closed test as well. So look at the green one. Okay, we can still randomly select the 15% of the tokens, right, and replace them into mask. It is a special token. So at the corresponding output, okay, you can see that the third token is replaced by mask, okay, special token. So we can use the output of the third token, and after that we create a very simple MLM classifier, and the classifier will output a softmax value to identify which word in the dictionary that mask token should be. So there at the green one, okay, take a look at the green one. There is a path to fine-tune the red weight to green weight, and the green weight is fine-tuned by using cybersecurity document, by using the MLM task. Okay, and there's an interesting thing is that sometimes it is very difficult for you to train the red weight to green weight, because the red weight contains millions of parameters, and these parameters are trained by billions of documents and sentences. So if you're a cybersecurity document, maybe you have only hundreds or thousands documents, so it is very difficult for you to use such kind of the green process, okay, to use the MLM process to fine-tune the red weight to green weight. Okay, so one of way to do so is that in this neural network, you can frozen some weight take this example. We can frozen the very first few layers of weight, okay? And for example, you can take the last 4 layers and make them trainable. So when you perform MLM, the green process, the frozen, or we say non-trainable weight will be freezed. They will still the same, okay? But only the last 4 layers, or you can design your process. Only the last 2 layers, 4 layers, or even 1 layers are trainable. So that is easier for you to perform such kind of green fine-tune processes. And after that, you have somehow optimized the grain weights, right? This grain weight contain more cybersecurity knowledge rather than the red weight. So after that, you can use the green weight. Okay, let's take a look at the purple part. Okay, after that, you can use the green weight to perform the further downstream task. For example, you can perform, for example, tactic or technique classification. You can perform any cybersecurity related classification by using the fine-tuned language model. Okay, so that is one of the way. However, it is still very you still need to collect a lot of cybersecurity documents. You still need to take some time to train the model from the red weights to green weight. And after that, you can train the purple weight to perform your downstream task. Okay, but it still takes some time and some computation to do so. Okay, so that is the first structure I'd like to share with you. That is the first one. Okay, so next, let's take a look at this one. Okay, this one is the second structure I'd like to share with you. Is that since we think the weight of the language model are quite large, right? The amount of the weights could be millions or even billions. So the second idea is that we've frozen the entire language model. So it's very similar. So take a look at the black lines and blocks. It's still the original one. We have text file, we have a tokenizer, which is not shown in this picture, and we have word pieces, and we have language model. So we simply just use the output of the COS as the representation of this sentence, this document, right? So after that, we can attach a neural network, but make sure the size of the input, the green one, okay, is exactly the same as the size of the output of the language model. For example, 768. And you can design your own neural network, recurrent neural network, dropout, convolution, autoencoder, whatever. Okay, you can design your own neural network, but the output, we recommend that the output of your the green neural network is still 768. So that we frozen the red weight, and we use NLP, okay, attached after the language model, and the output is still the same. The dimension is still the same, but we use the green output as a transformation. Okay, but how do we train this green weight? Okay, so in these cases, we also need to attach another downstream task. For example, the purple one, it is downstream task. It has a task to do. It is a classification problem. So when you train the purple weight, okay, make sure your partial differentiation, your gradient descent, include the green structure. So that in this case, the language model simply just output the representation, okay? But the representation, the the black output, will be transformed by the green structure, and the tangent space of the green structure, okay, will further be used as the input of your classifier to perform some kind of classification. So in these cases, you don't need any other cybersecurity document. You simply just need a MLP layer and the classifier, the purple one and the green one. But I have to mention that the green lantern space right here, it is a kind of transformation from the black output to the green vectors, right? But this green output, since it is trained by the purple task, so the lantern space, the green lantern space, is not like this one. Okay, think about this one. When we output the green lantern space, in this picture, that is the COS output. The COS output is trained by English text, right, and by the cybersecurity document. So the output of the COS is it still knows what English is, and it knows additional cybersecurity knowledge. But when you train this model, the purple structure is not involved when we fine-tune the weight, the green weight, by using the green process, right? It is separated. The training of purple structure and the green structure is separated, okay? But you take a look at this one. If you don't do MLM or closed test, if you don't have additional knowledge to train your language model, and then you have only one downstream text, which is the purple one, then you have to train the green part by using the purple structure. Okay? And of course, if you have additional cybersecurity document, you can train the green part by using MLM, and this in this green structure is outside the language model, which is okay. Okay, which is okay, but I didn't show it right here. Okay, but if you don't have extra cybersecurity document, and you have only one purple downstream task, and then you have to train the green structure by using the purple structure. But if you indeed have additional cybersecurity structure, you can train the green structure in this picture by using MLM, but not the downstream purple task. Okay, so that is this one. Okay, the third one I would like to show you is this one. Okay, again, the black one, we have text, we have a tokenizer, and we input into the machine, the language model, and we have n different layers, and the output is the representation of the sentence. Okay, the black one is that. Okay, so there's another structure, what we call LoRA, L-O-R-A. It is designed by Microsoft. Okay, so the idea is that since we cannot, since it is very difficult to modify or to train the red weight, right? The red weight. So we frozen the entire red weight. But okay, take a look at the green. We split the language model somewhere. Okay, but it's really but you can design any structure. Okay, you can split it any place you like. Okay, LoRa allow you to do so. So let's take an example. If you split the LoRa at the green line, okay, so when you process when the language model, it has n different layers, right? But you split at somewhere. So let's assume that you split at certain structure, and the output is 768, and the following layers, they accept a vector of 768. So the LoRa means that originally the vector will pass to the next layer, right? So we have a black line, black arrow right here. But the LoRa means you create another neural network structure, okay? And take a look at the red arrows, okay? You use the output of the previous layer, 768, and use it as the input of the LoRa. And after some calculation, okay, the LoRa has a green weight, okay, it also output another vector, which is the green arrow, and the dimension is still 768. And after that, take a look at the pairwise addition. You simply just add the original vector and add it with the green vector, which is a processed vector by LoRa. But the input is still the red one. So you add the green one, which is the output of LoRa, and the red one, which is the original vector. And the pairwise addition is the purple one. And in this case, you don't have to train the entire language model, which is the red weight. You simply just add an additional structure, which is LoRa, and use some output of certain layers and try to modify it by the LoRa and add the output of LoRa to the original vector, and the purple vector will continue process in the language model, and so on and so forth, so on and so forth. And after that, you can use the and in order to train this green LoRa model, right? So the red language model weight will not be changed because it is frozen. But in order to train this green LoRa, you still need to design your downstream text, which is the purple one, the purple weight. Okay, so when training the purple weight, the green weight will be trained as well. In this case, the LoRa means low rank. Low rank means there are only very, very few parameters in this green structure. Okay, so it is more easily to train the LoRa model. Let's take a look at the right bottom side. Okay, we draw something. Okay, for example, if the dimension is 768, okay, and the original vector, okay, right here is the red one. Okay, I have a lot of red data point right here. Okay, a LoRa means we use the red vector as the input and generate the green vectors, and we add them together. So on the linear space, it is the purple vector, right? The green one add the red one, and it becomes the purple one. So it will move the original data point, which is the red data point, to some other place in the same length space. So in this case, when you perform downstream task, which is the purple neural network, the input is not the red data, it's the purple data. And we believe the purple data after training, the purple data can perform well in the purple downstream task. So that is LoRA. Okay, and in this class, because we find some very useful and interesting LoRA explanation on network, so I will provide some interesting video in our class YouTube list. So after this video, please take a look at the some videos provided by other YouTubers or classes. Okay, and I also include one short introduction to LoRA made by the Microsoft. Okay, it is the first author of the LoRA paper. So let's see how he introduced his excellent work. Okay, let's stop right here.